Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This is our final video lesson for Thermodynamics 1, and we're going to be wrapping up the topics in Chapter 8 on modeling phase equilibrium for pure components. To be fair, this really deserves a lot more attention and time than this, but because we cover it in Thermodynamics 2, I am just introducing it to you so that you'll be familiar with the language of Thermo 2. So these final topics are not going to be on our exam or have any homework over them, but I do want to introduce to you the thermodynamic concepts of chemical potential and fugacity. And then, because students ask all the time, I know that there are other phases, yes, but yon being just a solid, a liquid, and a gas. And so I will give you some pointers on where you might look for those, and also very briefly discuss why we don't include those in our materials in our thermodynamics courses. So first, let's talk about the phase equilibrium criterion. We had mentioned earlier that the phases would be in equilibrium when Gibbs energy was equal to 0, and then I just kind of dropped it at that point. Now what that says is that if dg is equal to 0, then if I have two phases, alpha and beta, then the Gibbs energy for those two phases will be equal to each other. Frequently, we define the chemical potential as mu, and it is how Gibbs energy changes with the number of moles of substance at a fixed temperature and pressure, okay? Now, for a pure substance, this isn't really all that exciting. It's much more interesting when you get to mixtures of components, where if you change the number of moles of something, you are also changing the composition of the mixture, right? So that's why this topic is really primarily for our Thermo 2 course. But let's work with this, because chemical potential you should have been introduced to in a chemistry class also. And what this tells us is that if the Gibbs energy is the same in both phases, right, dg is equal to 0, then that also means that chemical potential needs to be the same for the two phases. Okay? Now, it's a useful thing, but yeah, it's really actually hard to work with, really hard to work with. So we can transform this mathematically by just applying a continuous function to this variable, okay? And that turns chemical potential into what we call fugacity. Now, fugacity is defined as the difference between the chemical potential that we are looking for and the chemical potential at a fixed state 0. Okay, and it is by definition RT times the natural log of the ratio of the fugacities at the state we're looking for divided by the known state. Okay, now that would be for a mixture. We put a little hat on it. We're only dealing with pure substances, so therefore I can remove the hats. And this is then the partial molar Gibbs energy. More on that in the next course. Okay. This state with the little superscript 0 on it, that's going to be our reference state. And that allows us to do calculations even though we don't really have any defined 0 for this, okay? And so therefore we need to define a reference state. Fortunately, the inventor of fugacity, G.N. Lewis, said, well, wait a minute, gases behave like an ideal gas as the pressure goes to 0. Therefore, the limit as the pressure goes to 0 of fugacity of a pure substance divided by the fugacity at its reference state will be 0. So the fugacity of a substance is going to go to its ideal gas behavior. Did I say that would be 0? It's equal to 1. Sorry about that. The word itself, fugacity, comes from the same root word as fugitive. And so what this is actually trying to measure is the tendency for a chemical to flee a phase. okay, right? It's a fugitive, it's trying to escape. The units are defined to be pressure units. And a lot of times we want things to be dimensionless, and so therefore we will divide fugacity by the pressure of the system to get a unitless version of fugacity, which is called the fugacity coefficient, phi. So what this tells me is if I have a substance that is truly at equilibrium, thermal equilibrium means the temperatures in all phases will be the same. Mechanical equilibrium says the pressures in all phases will be the same. And chemical equilibrium tells me that the fugacities of all phases will be the same. And so now then I actually have the complete set of the criterion for defining thermodynamic equilibrium. If we're looking at the vapor phase, we basically choose a reference state so that the temperature is the temperature of our system and the pressure is essentially zero, right? Low enough so that I have an ideal gas. And so at constant temperature, dG is VdP, right? Go back to our fundamental relations. And so this is equal to RT times the natural log of fugacity over P naught, my ideal gas pressure. And then I can choose an equation of state to use to evaluate the VdP. So for instance, on the screen I've shown what you get if you use the Pang-Robinson equation of state. But you can do this for any equation of state, and many of these are included in your book. For liquids, well, first of all, liquid's never going to be an ideal gas, right? Because it's a liquid, it can't ever be an ideal gas. So to determine the liquid phase fugacity, we're going to start by noting that I have equilibrium if I have vapor saturation, right? So at the temperature and the saturation pressure, the fugacity of the vapor is going to be the same as the fugacity of the liquid, which is the fugacity at saturation. And we have ways of estimating the vapor fugacity, right? I can use an equation of state or whatever. And so therefore the fugacity of the liquid would be the fugacity coefficient at saturation times the saturation pressure. Did I mention that vapor pressure would come in very handy on doing these calculations? It will be handy throughout Thermo too. So then if I have any other pressure, all I'm going to do is a pressure correction. And that turns out to be that I take this saturation value, phi sat times p sat, and then multiply by the exponential of the integral from the saturation pressure to my given pressure of the volume as a liquid over RT dP. And this is called the Poynting pressure correction, and very useful. So I'm going to do the gas calculation at saturation, and then I'll increase the pressure, but I need to do the gas calculation at the correct temperature. Okay? So that would be how you would do this for a liquid. For solids, well, actually, okay, solids just don't really change too much. If it's at low pressure, it's going to be very close to the fugacity of the solid is going to be very close to the saturation pressure at that given temperature, and don't even worry about the pressure. If the pressure is very high, then yes, you need to do a correction. And so the fugacity for the solid phase would be the vapor pressure, or excuse me, saturation pressure, we're talking about solids here, times the exponential of the volume of the solid times P minus P at saturation over RT. Now, my final topic that I wanted to do is I just always end up with students saying, but yes, there's more than just solids, liquids, and gas or vapor. And so, yes, there are a lot of these, but I've got some videos here that I'm going to recommend that if you are interested, you can watch these. But for instance, plasma is actually very important phase. But it isn't significant in the kinds of chemical production facilities that most of us end up working with. And so therefore the thermodynamics of plasma is just not as necessary for us to cover. But if you want to learn more about plasmas, I've got several videos here that you might be interested in. And finally, the other one that's of interest is the BoseEinstein Condensate. Now, there are others, okay? This is not a comprehensive list of all the other phases, but plasmas and Bose-Einstein condensates are actually, they do have some significance that you may be interested in. And so again, I have some videos that I might recommend for that. And then finally, this last video is some of the more obscure states of matter that might interest you. So this concludes our study for Thermodynamics 1, and I thank you so much for studying this with me.